In 1885, a Swiss schoolmaster named Johann Balmer made a groundbreaking discovery about hydrogen. He measured the absorption spectrum of hydrogen, revealing something fascinating. What caught his attention was the pattern of discrete lines at specific wavelengths. These lines weren't random. They could be predicted with a mathematical formula. Now, you don't need to dive into the details of that formula just yet. But think about it. A hydrogen atom with just one electron has this unique spectrum. This observation opens up a world of understanding about atomic structure and energy levels. It's incredible how something so simple can lead to profound implications in science. So let's talk about electrons and energy levels. Did you know that electrons can only occupy specific energy levels? It's like they have a set of stairs they can climb. Imagine trying to climb a flight of stairs. You can jump up 1, 2, or even 5 steps if you're feeling energetic. But you can't just float halfway up a step, right? That's how electrons work. They have quantized energy. They can only have certain amounts of energy, nothing in between. And the gaps between these energy levels? They also have defined values, just like the steps. When an electron jumps between levels, it's like jumping from one step to another. There are many combinations, but a finite number of steps. So, next time you think about electrons, remember their stairway to energy. Let's talk about the atom, specifically the hydrogen atom. Imagine an electron orbiting its nucleus, like a tiny solar system. In this model, the nucleus is the sun, and the electrons are the planets. It's a helpful way to visualize how atoms work, right? But here's the catch. This model has its limits. As we dive deeper, we'll see why it doesn't hold up perfectly. For now, though, it helps us understand quantized energy levels. Electrons exist in specific energy levels, not just anywhere. This concept is key to grasping atomic behavior. Let's dive into a fascinating concept from the 19th century: wave-particle duality. You see, particles like photons and electrons can behave both as waves and as particles. It might seem strange that a particle's energy is quantized, right? But if you think of an electron as a wave, it all starts to make sense. Imagine waves in the ocean. They have specific frequencies and energies. Just like that, electrons can only exist at certain energy levels. This dual nature is key to understanding the quantum world around us. Imagine a taut string, like a piano wire, stretched tight at both ends. This string has a fundamental frequency, a unique sound it makes when plucked. When you hit or pluck it, it vibrates in a specific pattern. Picture this, a snapshot of the string in motion, captured in time. Now, think of a blurred image showing all the places it might be as it vibrates. It's like taking a photo with a slow shutter speed, revealing its dance. This is the beauty of sound and motion, all in one string. But this isn't the only way a string can vibrate. Check this out. The ends of the string are still, but there's also a point in the middle that stays put, called a node. This setup changes everything. The wavelength is now half of the first vibrations, doubling the frequency. Musically, this means it sounds an octave higher, known as the first harmonic of the fundamental. And it doesn't stop there. We can have even more allowed vibrations. The third and fourth possibilities create further harmonics, expanding our musical range. Even if this concept of music and physics is new to you, let's dive in. Imagine a vibrating string, bound by fixed ends. It can only adopt specific frequencies, like a musical note. These frequencies are quantized, meaning they can only take certain values. Why? because the wavelength must fit perfectly within the string's length. And here's the cool part. Frequencies are tied to energy levels. So the energy of a vibrating string is also quantized. It's a fascinating dance of physics and music, all intertwined. Imagine an electron as a wave, and suddenly its energy values make sense. Visualize it orbiting a nucleus like a string looped back on itself. This helps us understand why only certain wavelengths are allowed. Each wavelength corresponds to a specific frequency. And those frequencies, they have energies tied to them. This gives us a clear explanation for the quantization of an electron's energy.